Mrs. Anna, I can't hear anything.
Because I was muted.
Oh, okay.
Okay, let's pretend you found some odd powder on the counter and you don't know it's sugar, but it is. You take that sample, it's a white powder, and you put it through a mass spec, right? So a mass spectrometer, you're going to take that substance, you're going to put it in some water, it's going to dissolve. Can you guys see my screen?
Yeah.
Yes. It's going to dissolve, and then the mass spec will heat it up and turn it into gas, right? So let's say your sugar looks like this. C with, I don't know, that's the bonds with some H's and O's. Okay. The mass spec will shoot an electron beam towards it, so energetic that it will knock these electrons loose, and it will break all the bonds. So what you have are just some carbon with a positive charge because the electron came off. You have some carbons flying around, some oxygen flying around, some hydrogen flying around, and it flies through the mass spec, and the mass spec detects it by its mass. Okay, tell me, what mass is hydrogen on the periodic table?
1.008.
Yeah. So on this, you would see a peak, right? Tell me all the 3 peaks that you will see.
Around 1, around 12, and at 16.
Got it. So you'll see a peak around 1. Ooh, that's 1. You'll see a peak around 12 because carbon weighs 12. Oh. And you'll see a peak around 16. But this peak would be double the height. Ah. And of course, on this side will be the percent abundance. Abundance. Why is that double the height? This is hydrogen, by the way.
Because there's double the amount of hydrogen?
Yeah, you have double the amount of hydrogen. As you can see, the ratio is for every 1 carbon, it's 2 to 1, right? 1 to 2 to 1. So you're going to get a peak of the hydrogen double the amount of those, okay? From the mass spec, you're going to deduce that you have for every 1 carbon, you're going to get 2 hydrogens and 1 oxygen, right? 1, 2, 2 to 1. This is called the empirical formula. The empirical formula right here. And that's all you can get from the mass spec. But your substance, it's not that, is it? That's something else. Your substance is this. How am I going to know what my substance is if the mass spec gives me this? Any suggestions?
You can multiply the mass percentages by 100 grams to find the actual molecular formula.
Oh, yeah, you can do that. But you know what? There's an easier way to do it. Oh no, I'm gonna have to give you the mass of your for your molecular. I'm gonna give you that mass. Okay. Let's say your mass. Okay, first you have to know the mass of this guy. This is the mass of the empirical. What's the mass of 1 carbon, 2 H's, and 1 O? You guys calculate that. Go.
$30.03.
I got 30.03 like you. Yes, good job. So the mass is 30.03. Let's say my mass is 90 grams per mole. So what can you say about 30 and 90?
You divide them.
That's what?
You divide 90 by 30, and then
Yeah.
it's 3.
It's 3. It tripled. that means the subscript triples. So it's C3H, triple that, 2 times 3 is 6, and then O3. Okay, so that is my molecular formula. So this must be 6 times, so it's 180. So if it were 180 grams per mole, then you would say, oh, that's 180 divided by 30 would be 6, so you multiply all the subscripts by 6, okay? Notice the subscripts are the number of atoms, 6 atoms, 12 atoms, 6 atoms, right? If we can't count atoms because they're too small, we're going to count 6.022 E23 atoms at a time, which is equivalent to 1 mole. So 6 times this is 6 moles. So those numbers, the subscripts, are also corresponding to moles. So if I give you a problem that's a CHO, and it's saying, give me the empirical formula, you shoot it through a mass spec, you get some numbers, and you have to convert whatever they give you into moles somehow. Okay, that's the goal in getting these formulas. Is that clear? So the empirical formula gives you the smallest whole number ratio, smallest ratio, and the molecular gives you the actual. This is the real substance, what it actually looks like. Okay, so let's do some problems. Okay, now let's do 3.14. Everybody go to your spirals. Go to problem 3.14 that you did last night. How did you feel about these problems? Were they easy?
Yeah.
Yeah, they're fairly easy, right? Should I go over? I'm gonna go over it anyway, just to make sure that you guys get it. So this one, the empirical formula they give you. So obviously they got that from a mass spec, right? C3H4. When they give you, that's the C3H4, right? And they tell you the molecular weight of the actual substance. This number is not the empirical, it's the actual. That's called the molecular formula. And you don't know what that is. So they gave you the empirical. You don't know what the actual is. The actual substance can be that, or C3H4, or you can double it, C6H8, or C triplet 9H12. We don't know. But they gave you the mass. So the mass of this is equal to 121 atomic mass units. So all we have to do is get the mass of this. And then we compare. Okay, what's the mass of C3H4?
40.06 AMU.
So you add them, and she got 40.06. 40, let's just say 40. Okay, so can you compare those? What happens?
It was tripled.
It's triple, yeah? So all you have to do is triple the subscripts. Triple the 3, you get 9. Triple that, you get 12. Oops. C9H12 is the answer. In the book, they have a formula. The N multiplier is the molar mass of the molecular over the molar mass of the empirical. So you're going to get 121 divided by 40. I don't ever use this formula. I just see you tripled or whatever. And it triples. That's what that is. That's what that means. Okay, fairly easy. Okay, let's do this problem. So when they shot this through a mass spec, it didn't give them grams. Remember, this is vitamin C. It has CHs and Os. So it has carbon, it has hydrogen, and it has oxygen. And they want to know what is the empirical formula. So they want to know these numbers, right? What do those numbers stand for again, the subscripts?
Moles.
Yeah, you need moles. And so you go to the mass spec data and they gave us percentage. You're going, how do I get percentage to moles? How do I do that? Does anybody have an idea?
Multiply by 100 grams.
Yes. So you're going to pretend that you have a 100-gram sample of vitamin C. You can have 200 grams or 500 grams. It doesn't matter. I chose 100 because what is 40.92% of 100? It's like I can do that.
40.92.
Yeah, so that's why I use 100 grams. You can use whatever. So I'm going to do, I have 40.92 grams of this. I have, that's 100 of that. 4.58 grams of this. Times 100. Oh my gosh, my pen. 54.50 grams of that. Okay, everybody change all those to moles. Go ahead on your own. See if you can race me. So slow. Oh my gosh, so slow. Okay, notice here I'm not using O2 because this is a part of the substance. It's not O2, it's just an O inside this vitamin C. Somebody give me all these numbers quickly, please.
The carbon is 3.407 moles. The hydrogen is 4.54 moles. And the oxygen is 3.406 moles.
Okay, so do you see how it looks like it would be like a 1 to something to 1, right? Because these look the same. So if you have 2 to 4 boys to girls, what's the real ratio?
1 to 2. 1 to 2.
1 to 2. So how did you do that in your head?
Divide by 2.
Divide both of them by the smallest number to get 1 to 2. You're going to do the same thing here. Divide all of them by the smallest number. Divide by 3.407. Divided by 3.407. So it's 1. What is this number?
1.33.
Okay, so if you see a number that's right, like a exact third, or like 0.25 or 0.5, you can't put those numbers, you can't round them. So what you're going to do is you're going to multiply it by a number so you get a whole number. What would that be?
3.
Yeah. So multiply all of, if you do that to 1, you have to multiply it to all of them. So it would be 3 to this 4. So the answer would be 3 here, 4 here, to 3. Those are the mole ratios. Pretty easy? Okay, so this one, any questions so far before I keep going? Okay, so this one is the same thing, but you don't have a mass spec. What you have is this big furnace. So instead of sending it through the mass spec, you're going to burn it, okay? When you burn it, let's say it's a hydrocarbon, let's say it's methane is on your stove, right? If you put it through this machine, it will combine with oxygen when you burn it. So burn, burn, burn. When it burns, the oxygen will oxidize the carbon, and it will make a very stable substance with carbon called CO2. Okay? And then the oxygen will also oxidize the hydrogen, and it will make another stable substance with H and O's. What is that?
H2O.
Yeah, very stable. Okay. So then when you run it through the sample, this, when it comes out, you're going to get the CO2. You're going to catch all the H2Os over here. Okay. And you're going to wait before and after. You're going to get the grams of H2O. And then this one will catch the CO2 that you make. You're going to weigh it before and after, and you're going to get the CO2. Okay. So once you weigh it, do you see the H's in there? You're going to find how much H is in your sample so you can get the subscript for the C, the H. Let's say this is CHO, like an oxygen. It doesn't have to be with oxygen, but let's say it has CHO. Let's say CHO substance. You're going to try to get that. Once you get the grams of that, you can get the grams of the H. The grams of this will give you the grams of the C because you trapped it in CO2. Okay, and then the O, I'll show you how to get that later. Now you're wondering, well, what is this? This gives you extra O minus 2s. Let's say you put your substance in and you try to oxidize it by burning it and you only get carbon monoxide and it comes out as carbon monoxide. You need to be carbon dioxide, right? So this O will give you extra oxygen to make sure that you have a complete combustion all the way to CO2. Okay, so when you have a heater in the house, it'll burn the water and you're gonna get some carbon dioxide, but sometimes if we don't have enough oxygen, it'll go to CO, carbon monoxide, which binds with your hemoglobin stronger than oxygen does, and then it causes you to suffocate, right? So this is called incomplete combustion. You need the carbon 2 oxide to oxidize it all the way so it's CO2. Any questions on that apparatus? Okay, once you get those numbers, then you're going to do the following. Here's an example. Everybody look at sample exercise 3.15 in your book, in your homework last night. Okay. So the title says, you want to know the empirical formula by burning it, combustion analysis. And what you have right here is C's, H's, and O's. And you want to know what this is, and what this is. And the way you did that is you burnt it, right? When you burnt it, you used 0.25 grams of that whole thing. So all of it together is 0.255 grams. So that is the mass of carbon, the mass of H, and then all the H's that you got and all the O's you got, that's a total mass, 0.255. That's this number, okay? Then it also made this much of the CO2 because you weighed that part of the apparatus before and after, right? So you got 0.561 grams of CO2. You guys are writing down whatever I write down, right? And you also got 0.306 grams of H2O. And they didn't tell you how many grams of oxygen there are. Because, do you see the numbers? This is CO2. This is H2O, but they didn't give you oxygen. Okay? So we'll see if we can find that later. Okay, those are the givens. Any questions on the givens? Okay, so my goal is to find the moles of carbon. I'm going to use this to get carbon out of it. To do that, I'm going to convert this to moles. 44.01 grams of CO2 is 1 mole of CO2. Okay, I don't care about CO2, I care about carbon. So inside a CO2, CO2 looks like this. How many C's do you have?
One.
One. For every 1 mole of CO2, you have 1 mole of C, because I see 1 in there. Does that make sense? So that will give you the moles of C. So what is that?
0.153 grams of carbon.
Grams? I don't want grams. How did you get grams if you're only?
Sorry, I went over.
You went over. The book goes all the way to grams, right?
Yeah.
You don't have to do that yet. This doesn't make sense. It makes sense to me to go to moles first because those numbers are in moles. So tell me that in moles.
Okay.
It's 0.0127 moles.
Moles of what?
Carbon.
Yes. Okay, so we're close. We got 1. Now we're going to do the H's. Go ahead and do this yourself. Let's see if you do it right. Okay. So inside an H2O, here's H2O. For every 1 H2O, how many H's do you have?
2.
2. 2 H's inside H2O. There you go. What's that?
0.0340 moles of hydrogen.
Okay. So now I have the second number, the second subscript. Now I need the oxygen. Any suggestions on how I do that?
Subtract the moles of C and H.
From what?
Oh wait, first you get the grams and you subtract it from the 0.255 grams.
Okay, so here's the idea. Perfect. So if you add the grams of O and the grams of C and the grams of H, you add them all. What do you get? What's the total mass?
0.255 grams.
Yep. Because they give us that up here, right? It's right here. Okay, so we just need this grams of carbon. So I'm going to do it over here. Go ahead, everybody, change them both to grams. That's why she gave me grams earlier. Is it 1 mole is, do that yourself. Don't wait for me because my pen is like really lagging. It's killing me inside. It's so slow. I'm dying. 0.03. Oh my gosh, so ugly. Okie dokie. So how many grams of C did you get?
0.153 grams carbon.
0.153 grams carbon. And the other one?
0.0343 grams hydrogen.
I got 0.0342. 3 is fine, whatever. Not it's pretty okay. Let's see. This is hydrogen, right? Okay. So then over here you're gonna put carbon is 0.153. Hydrogen is 0.0342. And you don't know what this is. So what's that? Somebody.
0.068.
0.0678, right? Of
Yeah.
O. Yeah. So that's oxygen, single oxygen, right? Okay. Now what we're going to do is change them all to moles, so then we can divide by the smallest one and you can get the ratio. So change this to moles. Go ahead and do that. And do it all yourself, divide by the small number, and tell me the empirical formula, please. Okay, what is this?
Point 0042 moles of O.
Okay, don't truncate it too soon or round too soon, because you have 3 sig figs. I would 0.0424. That's what I would put in.
Okay.
Okay, now you're almost close. You're almost there, but these ratios need to be in whole numbers, right? So what do?
Divide by the smallest mole.
Yep. Divide by the smallest mole, 0.00424. 0.00424. Whatever. Ugly handwriting. This must be a 1. What is this one?
7.1.
7.99. I can round that to 8. And then this one is
3.
Yep. Okay, so the empirical formula is C3H8O1. Questions? Make sure that you know that's the empirical. They have to give you more information about the molecular. Exactly what information do they need? Do you need?
The mass.
Yeah. The molecular. Questions? Okay. That kind of question, this is like the hardest question. One of the hard, yeah, for this chapter, it's like the hardest question on the AP exam. If you can do that, it's not so hard after all. Hard for other people, not for you. Okay? So, limiting and excess reactants. This, if you match these two, you'll get, what do you get when you put 2 H's and an O?
H2O.
H.
How many H2Os can I make?
3.
I can make 3, right? Why? Why can't I make 4?
You're out of O's.
We're missing an oxygen molecule.
You're out of this. You're out. That means that your reaction will stop. That means the O just limited your reaction. It limited it from continuing, didn't it? Bad oxygen. That's called the limiting reactant. LR. Okay? And what happens to the hydrogen? You have excess, right? This is called the ER, excess reactant. Okay, so over here, the limiting reactant determines how much you make. You only had 3 O's, so you only make 3 waters. Got it? Okay. So go to your sample exercise 3.18. Tell me how you did this problem. Guys, how did you do this problem? Emily, how did you do this problem? Emily, battle?
Oh, I got a little confused on that one.
I know. And does anybody else confused?
I got a suggestion. I don't know if it's exactly correct. Can I say
Okay.
it?
Go ahead.
Would it be fine to separate NH3 and try to find the moles of each atom? Well, not atom, but like each part of the molecule, and go little by little?
Yeah, so you want to take the NH3, like separate it out, and then you'll match the N and the H?
Yeah, exactly.
Yeah, kind of. I kind of see where that's going. Anybody else have another? That one's kind of hard to do. Yeah.
You can use the molar ratio of 1N to 2NH3 and 3H2 to 2NH3 to find the moles of NH3 that each amount will make.
Yes, that's exactly what you're gonna do. You're gonna see using the ratio like how much you'll make. Okay, so first let's write down what we have. It says you're gonna make ammonia. You want to know how much you'll make if you start with, I'm gonna put, everybody write this equation down on your paper and leave space in between them. I'm going to teach you a shortcut, okay? You guys like shortcuts? Okay. Put a line down here where the arrow is. Put a line here as well. Put a line here. You're making a table, okay? Or a chart. Okay. This is called the chemical reaction. Okay, that's the reaction. Okay, it says that you have 3 moles of N2, right? So I'm gonna put it here, 3. I'm gonna write moles up here because I don't want to put moles in every section. It makes this table like cluttered, and it makes it harder to look at. And then you have 6 moles of this, right? For the H2. I'm gonna put 6 right here. This is called initial. So I'm going to put initial. So that means in the beginning, they mix these two things in the beaker, right? Did they put any ammonia in the beaker, according to the question?
No.
Yeah, just put a 0 there. Because they didn't give me a number for it, so that means they didn't put any in there. Okay? So now you're going to use these ratios. There's a 1 right there, a 3 there, and a 2, right? That means I'm going to put a in blue. Okay. I'm going to change this. That means I'm going to use minus, I'm going to use 1 mole of this. I'm going to use 3 moles of this. And I'm going to, like, minus 3. And I'm going to make how many moles of ammonia?
2.
Yeah, 2 for 2. That's how it changes. Okay? You can use multiples of it. Like, you can use 2 of these to 6 of these and make 2 of these, right? So I'm going to put an X there because you can use multiples of it. You can make more than 2 moles. You can make 4 moles if you had enough, right? So that's the X. Okay, bear with me a little bit on that. I know it's a little bit confusing right now. But do you understand the -1, -3, and +2?
Yes.
Good. Okay. What I'm going to do is I'm going to put a number here. So I'm going to pretend that one of them I ran out of it. Let's pretend I ran out of N2 in the end. So what would X be if I ran out of it?
Three.
X were 3, right? 3 minus 3 equals 0. Okay. If X were 3 right here, plug in 3 right there, what would you get?
9.
What? Negative, no, yeah, -9, you get -3. Okay. So you can have a negative number. This is what you'll make in the end. Or sometimes we call it at equilibrium. That means in the end. Okay, in the end. You can have a negative number. So I'm going to erase this. I'm going to pick another X. What's another X that could be possible? What if I try to make this 0?
2.
2? Okay, let's try X equals to 2. Okay. This 3 times 2 is 6. 6 minus 6 equals 0, right? Over here, what would that be?
1.
1. Because that's 2 times 1 is 2. 3 minus 2 is 1. What would this be?
4.
4. Okay. If X were 2, this means that I used up all the H2 and I have no leftovers, right? That makes sense? Here, this one is an excess. I have 1. It has leftovers, okay? This stands for mole. That means I have 1 mole of N2 left over. What does this 4 stand for?
Product.
Yeah. What's my product?
Ammonia.
Moles of ammonia. Okay, so you see what I just did? So if they ask me, well, how much ammonia will you make? You're going to say what?
4 moles of ammonia.
Yeah, so you're going to say, in the end, I made 4 moles of ammonia. And if they say, well, how many grams did you make? Just convert that to grams, right? Over here, you're going to say, they're going to ask you, which one is your limiting reactants?
The hydrogen.
Yeah, because you ran out of it and it stopped the reaction. And then this would be the excess, the ER. And if they ask you, well, how much left over do you have? Say, I have a mole of leftover. Do you see how easy this table is? And once you get used to it, you can just organize information really easily, and then you can answer any question they want. Okay? Let's try another example for you
I have
guys.
a question
Go ahead.
on the so here's what I got me confused. That initial reaction, are you basing that number on multiplying moles, like let's say H2, 3 moles of H2, so it's H2, therefore it's 2 H's, so 3 times 2 is 6, right?
No.
No, it's just example numbers is what you're giving us in that initial.
So the initial is right here in the problem. They have to tell me. They have to say, oh, I put this in the beaker, and I put this in the beaker.
Okay,
And
got
I
it.
mix them together, yeah.
Okay, thank you.
Okay, ask me some more questions, because if you don't now, it's gonna get more confusing in a minute. Okay, so let's go ahead. Everybody write this equation down on your paper. And then write it down. I always like to put space in between, because I put lots of gaps in between, so your table, oh my gosh. Okay, I'm gonna draw a line here. Draw a line there. Okay, I'm gonna title this is my reaction. This is initial. In the beginning, how much do I have in my beaker? Change, what's the change? And in the end would be E, or at equilibrium. Okay, can somebody tell me, how much do you have in the beaker?
$1,500 grams.
Yeah, of the oxygen, right? I better put that here. Or no. And how much oxygen do you have?
1,500 grams of oxygen.
Hydrogen, how much hydrogen gas?
Oh, 150.
150, perfect. Don't put it in the box yet, because I want to put moles in my box, because it's just easier. Okay, so if they give it to you in grams, what do you do?
Convert it to moles.
Yeah, convert both of them, please. Hurry, all of you, because you're going to do it faster than me. Okay, somebody give me numbers.
$74 moles for the hydrogen.
Okay, what's this one?
And 47 moles for the oxygen.
74 and 47. Okay, go ahead. And how much water was in there? Did they give you a number for water?
None.
Nope, so put a 0 there. Okay, and then go ahead and fill in the rest. See if you can do it yourself. The change. Okay, so what did you write for the change?
37.
No, don't put a number. Just put like this number right here.
Oh, minus 2.
2x. Put an x after it, okay? What's this one?
Minus 1x.
And this one?
Plus 2x.
Okay. Then you have to solve for x, so one of them is 0. Did you say 47?
37.
37? How did you get 37?
I divided 74 by 2.
Oh, yeah. So divide 74 by 2. 2 times 37 makes 74, right? So this is 0. Yes? So this one would be 10. Did I do that right? 47 minus 37. So how much water did you make?
$74.
Yeah. Questions on how we got those numbers? Questions on how you got x?
Is the X just supposed to cancel out the hydrogen?
So the x is supposed to cancel out one of the reactants.
Just one?
Just one. Like, I have to make one of them 0. That means I used it all up.
Okay.
So if I make x to be 47, I'll get a 0 here, but then I'll get a negative number here, so don't use that.
Oh, okay.
Any other questions?
Ms. Lozano,
Mhm.
does this always work using this little shortcut? Because if we use a longer molecule, will it still work for longer molecules with like that need lots and lots of atoms to make them up, or is this imperfect in some aspects?
It always works.
I'm worried if like every time there's always going to be that limited reactant and that excess reactant. And
Right.
if that's going to be like, because I know it was really easy to just divide 74 by 2 and then you get the exact number of 0. But what if there's not really a limited or excess reactant? Will there always be one of those?
One of them will always run out.
Okay.
Yeah.
Yeah, that makes sense.
Yeah, if the numbers are not that pretty, you can just do algebra. You can just do 74 minus 2x equals 0. And then you solve for x, and then you can get a number if it's not that easy to see.
All right. Okay.
Did I answer your question?
Yeah, pretty much it.
So just remember, these are all in moles. So if they ask you, the question is how many grams of water? Yeah, just convert it to grams. Which is the limiting reactant then?
Hydrogen.
Yeah, whatever is 0, because it ran out. And this is the leftover, so it's excess. Okay, so theoretically, you should get 74 moles, okay? That's called the theoretical yield. And that is what you get using stoichiometry. On paper, theoretically, you should get 74. But if you didn't get 74, let's say you only got 70, that's called your actual, okay? If you divide those from each other, it's blank, weird. Okay, let's say that theoretically you should get 74 moles. Put that in the bottom. And let's say that you only got 70. Put that on top. You multiply by 100, and you're going to get something called your yield, your percent yield. And you read about that already, right?
Yes.
Yeah, that's percent. Not this thing. I don't know what that is. Percent yield. Okay. Questions before we go to the homework? Okay, so if you go to your calendar, it shows you to click on this thing. It's called RICE method. The RICE stands for reaction, initial change, and equilibrium in the end. Okay, so you can, for the first slide, you do it like this. Okay, draw that equation, draw your table. For something like this is what I want you to do. Okay, this is the second slide. Okay, can you guys see that? Okay, can you guys see that well?
Yes.
Okay. So what you have here is they have a drawing for you. So it says, draw the mixture by mixing the two. You're going to mix them together, pour them into each other. Oops. Shoot. So sorry. Okay. So you're going to mix these together and you're going to make the bottom. Can you guys see the bottom part, the reaction? Okay. Do you see this right here where it says aqueous? That means these are not really together in water. That means they're separated. This little dot right here stands for Ag, and you must put a +1 because it's an ion. Okay, that's this right here. Okay, how many of those do you have?
4.
4. This right here is NO3 minus. You have to put the negative charge. How many of those do you have?
4.
4. Okay, so you have 4 of those. You have 4 of each of these, and then this is right here, K plus, and this is I minus. Okay. So when you make this, it tells you that you made AgI solid. You see the S right there? That means this Ag and this I bonded. And water can no longer separate them. It looks like a solid. So the solid is Ag plus. Instead of the ions apart, they are now, remember when I made you draw the ions in the beginning? They're now stuck together in a crystal lattice, a bunch of them. Okay, but these, the K's, are still floating together. Got that? So when you draw the beakers, I want you to do the following. Draw the first one. How many Ags do you have? How many Ag pluses do you have?
4. 4.
Don't forget to put the charge, okay? 4 of those. How many NO3 minuses do you have?
4.
Okay, I'm asking you to write this instead because I don't want to count your circles. It'll take me forever. But you know what it means here. How many K's do you have?
4.
4.
4. How many I's do you have?
4.
4.
That's what you have in the beginning. In the end, it says that you have some AgI solid. So I'm going to make this a little bigger. Okay. So you're going to count the AgIs. 1. That's 1. That's 2. That's 3. And that's 4. Okay. And when you write it, make sure you put them together because it's a solid. You guys understand that?
Yeah.
So in essence, 4 of these canceled with 4 of those. They didn't cancel, I'm sorry, they bonded. So what else is left over? The 4K pluses are not bonded. You see this aqueous right here? That means they're not together, they're still apart. And you also have 4 3 minuses. And that's how you do the homework. Questions?
Wait, are we doing this on the? Is it like a worksheet?
Yeah, it's a worksheet. You put it on a piece of paper. You put your answers on a piece of paper.
Can you do it on the online, or does it have to be on paper?
Let me see. So there's no space for you to draw.
Okay.
But this one, there's space, but I would just write it on a piece of paper. It's easier.
Okay. Thank you.
Sure.
Is this going in our notebooks or?
No, you're just going to take a picture of it, and I don't know where you're going to put it. It doesn't matter. I just want you to turn it into Jupyter. So it says right here, it says homework, rice activity, turn in through Jupyter.
Can you go back to the example that you showed us just now?
Yeah. Oh, sorry.
Not that one, the one that you were working on.
Yeah, I see. Okay, go ahead.
Oh, thanks so much. Okay, I got it now. Just wanted to see something. Thank you.
Yeah. Okay, if you don't have a question, you're ready for the homework, you may log off. Oh, wait, let me take attendance. So the attendance will tell me when you logged in. It gives me a timestamp. Okay. So I took attendance. You may log off if you don't have questions. Otherwise, you may stay and ask me any questions you want.
Bye, Lozano.
Thank you, Ms. Lozano.
You're welcome.
Thank you.
Bye.
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 Bye, Ms. Lozano. Have a nice day.
Thank you, you too.
Miss Lozano.
Yeah. Yes.
Like whenever I enter the meeting, I'm always coming in as a guest.
Yeah.
And I don't have that problem with my calculus class, but I'm in like a class, like they sent me a join class code.